Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Long time.
Yes, it has.
It has been a long time, everybody.
Hello, everybody. How are you doing? Welcome to another episode of Ask Us Anything About Electrochemistry. I'm Alex. This is Neil. I've been out for a long time, and even coming back from a long vacation, I still couldn't actually be physically here. And actually, within the next few weeks or months, there will be a little bit more of a sporadic schedule with the Ask Us Anything About Electrochemistry live stream. Neil and I were just talking about it. We're not sure. We're both traveling
There's
different times.
Summer is just
all
one of
kinds
those
stuff.
times, right? It's like we have a mixture of some vacation
Mhm.
time and travel for work and
Yeah.
conferences and workshops. And yeah, I think the long and short is over the next like 2 months, June and July, basically.
Mhm.
We may or may not be here, or one of us will, maybe. So
I
we'll
may
do it.
even push it into August because there we have a bunch of conferences in August
That's-
as well.
Yeah,
So it could be even just September.
it's just one of
But
those things.
but we're here now, and I say welcome, everybody. We run a lot of we get a lot of emails, phone calls, YouTube comments, live stream, webinar questions about electrochemistry, and so we hold these about 2 hour long live streams where you can ask us anything about electrochemistry. We have answered a wide array of different questions, some very specific, some very broad, and we have found that the questions that we can best help you on are questions that are kind of in the middle, not so specific as to be like a very specific energy level associated with a very, very specific molecule, but not as broad as teach me cyclic voltammetry. For those, we have webinars and YouTube videos and content and other things for the bigger, broader subject questions. So questions in the middle will be answered probably the best, and we'll be able to spend a little bit more time describing it, answering it. Also, if you are a tier 1 or a tier 2 YouTube member, thank you for being a member. Your questions will get priority as we go through the questions. But generally speaking, just type the question into YouTube or into Twitter, because we're streaming on Twitter, and we will try to get to your question as soon as possible. So we run these for about 2 hours. If you're watching the live stream after it's done, we have the questions that were asked in the description of the YouTube video. So if you are watching this later, you can click and look through the description to find what question you may have missed and watch it. And Neil's actually been doing a lot of work collecting all of the questions since we've been doing these live streams. So if you are interested in I guess the Excel document that documents all these to look for, did we actually answer a question in a previous live stream? Just email us at pinewire@pineresearch.com and we'll be able to send that information to you. We try to keep it updated, and eventually we're going to be launching a website, new website, where hopefully that information will be just there and available.
Yeah, hopefully it'll be a kind of a searchable portion of our updated website at whenever that is able to be implemented, as Alex said. But for now, basically, I've made like an Excel sheet that has categorized every question in the 50 some odd episodes that we've done to this point over the past year. And you can search by a keyword. You can type your own keyword. You can search through a list of keywords to see. And, in episode 31 at timestamp 1 hour and 6 minutes, I answered a question about LSV. You can, click that directly to that timestamp. So if that's something that interests you, reach out to us and we'll provide that for you.
Yes. So I think there were maybe a few questions from my earlier that we may or may not have been able to get to, but there was one question that was asked, I think it was last week or earlier this week. It was just an email question. I forgot the person's name, but the question had to do with, they were doing some kind of experiment where they were maybe generating 1.5 milliamps of current, and they were able to observe that current in a cyclic voltammetry experiment or an LSV experiment. But they wanted to know that if they set the current range to something like plus minus 1 milliamp, and they received an overload error because 1.5 milliamps is above the 1 milliamp range, would 1.5 milliamps actually pass through? So this is a question of, does my instrument may have a current range that's the detection limit, but is the actual current that's being passed in the system, is that actually is that actually happening in my electrochemical system in reality, sort of say? Because you can always just switch the current range and you could then see that 1.5 milliamps. So why would it be the case that the 1.5 milliamps is not getting passed if I just have to switch the range? My original, to kind of answer this or talk a little bit more about it, I can share my screen to talk a little bit. I have my useful equation screen, but I'll actually be using something a little different. Is my, did it come up?
Yeah, it's doing the same thing where it doesn't automatically share you
Oh,
for
okay.
some reason, but I got you.
Oh, it's up. Okay. All right. So I might, of course, be rusty at doing all of this because it's been a while. But generally speaking, the current range, for those who don't know, if your working electrode is represented symbolically here, it's connected actually to a series of resistors that are in parallel. And there's actually, I can't draw resistors, but
You never know how many times to zag, right?
yeah, I don't know how many times to zig and zag in this thing. But each one of these resistors represents, and there's actually a little opening. So I can't erase it easily, but what I can do is I'll just make it like a different color. There's actually a switch. These open and close. These kind of open and close. And each one of these has some different value. This will be like maybe a 1 mega ohm, 1 mega ohm resistor. And then it goes by, and then maybe you have like just 1 ohm. And then you may have like, a kilo ohm or something like that. And so as current passes, and then what's happening is in parallel with this is some kind of voltmeter, something that allows us to read the display of what's going on. So it's like you can almost think of it as like an analog device where it's a meter and it moves across here. And so we know what the current is. And sorry, this is the working electrode. Just working the work. And so as current passes, what happens is current passes across a known resistor. We measure the voltage here. And because we know Ohm's law, which is that V is equal to I times R. If we know the resistance because we have this resistor, and we know the voltage because we're measuring it across this voltmeter, we can know what the current is. And this is how we generally measure the current. This is at least schematically the best kind of understanding and description. And so if you have current values of a variety, so let's say if this goes from 0 to 10 volts, then if I have 1 ohm versus 1 mega ohm, the current that passes will correspond to a different number if I'm on the 1 ohm range here or the 1 mega ohm range here, because I can only read between 0 and 10. Now there's a little bit more complication. There is what's known as a DAC or an ADC, analog to digital and digital to analog converters, because you're using a computer most of the time when you're using a potentiostat. So this is an analog device here, but in reality, it's something a little bit more like a digital device. Now, this is the best way for students and people to conceptually understand the current range. It's the reason why, if I have a lot of current and it goes into a very high resistor and I'm unable to measure something, or I measure something outside of this 0 to 10 volt range, then I'm going to get an overload error, or I'm not going to detect it. And it's simple to understand. I can adjust the current range, and then it gives me some other, a value that's within 0 to 10 that corresponds to an actual current that you're measuring. But it turns out that, when it comes to what actually happens, because there are reactions and stuff that are happening here, well, these reactions correspond to a current that we measure. But it turns out that there are other electronics beyond this. There's actually amplifiers to kind of amplify the signal. We don't always use all the resistors. We could actually use a resistor plus an amplifier to give us multiple current ranges. And so software and electrical engineers have actually done work to make it so that when you set the current range to say -1 milliamp to 1 milliamp plus 1 milliamp, even though you know that your reaction may generate plus 1.5 milliamps, if you only measure 1 milliamp, only 1 milliamp of current is actually being applied. And there are safety precautions because let's say you had 1 amp of current or 10 amps of current, you could damage a lot of the components. So there's a lot of other electrical engineering safety precautions that are implemented into a potentiostat design to make sure that the current that is measured in your, it within the current range for your potentiostat is the actual current that is happening or that is measuring. So even if your reaction in principle can generate 1.5 milliamps of current, it will only be 1 milliamp of current if it's hitting the range, the overload range of your system. There'll be things that will prevent it. So hopefully that answers that question or demystifies the idea that is the current range something that or is the current that I pass actually something that that's real, or is it another value altogether?
It is all fake.
Oh, everything's fake.
That's the takeaway.
Yes.
Okay, here. Did you disappear?
I may have disappeared. It looks like my internet connection's a little off, but I'm
Yeah.
reconnecting and
Okay.
whatnot.
Well, we're still connected because through my computer. Anyway, I just saw you went away. But,
Oh, okay.
but I can still hear you because my computer's fine, I believe. So anyway, there is a question here from Lingesh. Says, I'm not sure what WKT means here. Polarography is the old technique. Yeah, that's the term that was used. I don't know exactly which year, right? In that maybe 50 years ago or so, for what we just sort of call voltammetry now, or something along those lines. In any case, the crux of your question, it looks like, is the second part here. This is in the I versus E graph, so current versus potential. After a certain time, the current reaches a steady state value, but in CV it decreases after the maximum. Why? So essentially what it appears you're asking is, why do we get a peak, right, in a CV if the current goes up and then drops? So I can explain that actually as part of, I have a slides. I'll give you a bit of context from slides from a webinar that I have done previously. Oh, let me do the thing where I share the presentation and then.
Oh yeah, get the
'cause otherwise
presentation.
you won't see it.
Yeah.
I have to do this whole thing. Show this. I gotta show taskbar. I gotta go back here, and then let me know if I'm sharing the presentation.
Yes.
Okay.
Yeah, presentation's up.
Yes,
I'll minimize the question so
yeah,
that we
thank
can.
So I'll go through this a little. This is again material from a webinar I have given on basically rotating disc and rotating ring disc electrode, RDE, RRDE, Levitch, Katecki-Levitch, TAFL analysis. It's a whole 2-part webinar series. Recordings of that are in our webinars playlist on our YouTube channel for tier 2 members and above. If you would like to view all of those webinar recordings in their entirety, you can become a tier 2 member of our YouTube channel for any amount of time, just to let you know. But I'll kind of walk through a small portion of that to explain why we get that peak in a cyclic voltammogram. So it has to do with the interplay between kinetics and diffusion. So first is kinetics. And so the increase in current you get in a CV is due to kinetics. When you're scanning positively or negatively of the potential and the current starts to increase exponentially, that is due to kinetics. And so kinetics is the speed of an electrochemical reaction. First, we define what is called the overpotential. And so there is a standard potential associated with any faradaic process. And the overpotential is simply the distance from, away from, or greater than usually, that that Faradaic standard potential that you are. So if it, right, essentially over potential of 0 means I'm right at the standard potential of the reaction I'm studying. Okay, and I only bring that up because the over potential is used in the Butler-Volmer equation, which is the fundamental electrochemical equation used to define kinetics, and it looks like this. And so effectively we have current as a function of the exchange current, which is an intrinsic quantity, which is related to the electrode and the reaction. As you can see here, it is really more specifically, effectively, it's an extrapolation, I guess you could say, of the heterogeneous rate constant. Okay, but this is all kinetics. It's just like a kinetic constant of your system, and then you have this exponential formula in brackets, which are includes a transfer coefficient, which is basically a measure of the symmetry. Usually the assumption is this is 0.5. It's not always, but it is for a lot of systems. The number of moles of electrons that are transferred, and then a bunch of constants like Faraday's constant, the ideal gas constant, the temperature, and then of course our overpotential. Okay. Graphically, when we plot the Butler-Volmer equation in the absence of anything else, no diffusion, no mass transport, nothing, just purely kinetics. So this is an idealized situation. When we plot current versus overpotential, we get an exponential looking plot. And so it depends on the direction. So as I go positively in overpotential with the IUPAC convention, we have an exponential increase in current. As I go negatively, I have a cathodic reduction, exponential decrease or increase in the negative direction, either way you want to say it, in my current. And so that is the beginning of a peak that occurs in a cyclic voltammogram. It usually looks like this. The current starts to increase or decrease depending on which direction you're moving. The second part of this equation is mass transport or diffusion. Okay, this is generally random motion of ions in solution, materials, reagents, and usually it is characterized by movement from high to low concentration. That's kind of a driving force for movement. And so there's a lot of other concepts like the diffusion layer and the diffusion layer thickness, and then the bulk concentration. There's a lot of things I'm going to move relatively quickly over in the interest of answering this question quickly. The equation, however, which is the part that I want to focus on here, is called the Cottrell equation, and that is what is the ideal electrochemical equation that describes diffusion, just as the Butler-Volmer equation, as I said previously, defines kinetics. And so the Cottrell equation has this form, which is another function of another function for describing the current. This time it's as a function of time instead of overpotential, but we still have an equation that describes how current, in this case, is equivalent to the number of moles of electrons, a couple of constants, Faraday's constant, and then the area of the electrode surface, the bulk phase concentration, and then the square root of the diffusion coefficient divided by pi and the time. So basically we have is current is a function of time to the inverse square root. And when you plot that, it looks like this. It's a decay, right? Current versus time has a decaying characteristic as a function, as a consequence of diffusion. Okay. And this is neglecting kinetics and everything else. So these are looking at each of these processes independently. And again, I mentioned very briefly, but I'll just mention it again, is that the physical explanation for this decay is that the diffusion layer is growing, which means the path length of diffusion is getting bigger, which means that it takes longer for materials to make it to the electrode surface. And that causes a reduction in the current because there's less stuff to react. Okay. The diffusion layer thickness grows. So I'm going to skip this a little bit because I want to show you the peak phenomenon, right? As I said, stuff takes longer to get there. You get less current, but why do you get a peak? And so if you're scanning in a cyclic voltammetry experiment or LSV, a linear sweep, you're moving the potential in time at some rate. And as you do that, you increase your overpotential. Butler-Volmer kinetics dictates that I should have an exponential increase in my current. However, as I am running this experiment in this reaction, Cottrell diffusion equation dictates that I should have a decay in my current because the diffusion layer is growing as I am increasing my potential as well. And so basically, you get a peak simply because at some point in time, there's something has to give between those two phenomena. Kinetics is causing the current to increase. Diffusion is causing the current to decrease. At some point, there's a balance between the two, and you just physically get a peak. There's a lot more, of course, that there's equations that describe where that peak is and why and how much current it is in Randles-Sevcik equation and scan rates. There's a lot more there, but fundamentally, that is the explanation I can give you for the appearance of a peak when you do cyclic voltammetry under stationary conditions, is that you have a kinetic increase in current, the diffusion layer thickness grows, and diffusional effects cause the current to decay. And so a peak is just the natural graphical consequence of those phenomena. So I hope that addresses that question for you relatively quickly. As I said, I think I try to give a little more, detail in the webinar from which those slides come from. So I would encourage you to look at that webinar recording if you want to kind of have a little more context. But there you go.
All right, we have a question from Fernando. He says, hi, about electropolymerization of organic coatings on an electrode surface. Should I set the potentiostat for CV or have a constant potential? Any insight would be appreciated. And I just asked them a little bit more, just kind of questions about exactly what he's trying to do. And he's just trying to polymerize an organic molecule on the electrode surface, just having these organic molecules on the surface, and then at some applied potential, they react with each other to form a polymer. So I think, so the question is, do you just set a constant potential or do you run CV? Cyclic voltammetry is usually helpful when it comes to understanding at what potential do reactions occur. So as you sweep the potential initially, I'm assuming you're having your organic molecules around, kind of randomly diffusing, there will be a potential where you'll start to see either the oxidation or reduction reaction that allows the organic molecule to polymerize. But once it polymerizes on the electrode surface, my guess is that it's going to become a film on the surface, and it's not going to do very much. So you may run into a situation if you were to, say, set a constant potential. Setting a constant potential actually might be useful because nothing's changing, and you'll probably see a sharp decrease in the current. Like once the organic molecules polymerize, the current's going to fall off because it's going to become, it might be insulating. So CV, I would recommend mostly for diagnostic purposes, and I might even run multiple cyclic voltammograms. One cyclic voltammogram to see the initial polymerization, and then another cycle to see, oh, did the current of that polymerization decrease? And if it keeps decreasing with every cycle, that means that you're coating more and more stuff on the electrode surface. And eventually it'll probably just kind of flatten out and you've completely electrolyzed it. So that's one way to look at it. The only thing to keep in mind with CV is you might remove the polymer coating off of the surface if you're cycling back and forth, but you would observe that by seeing the opposite peak. So if you have an oxidation to form the polymer, and then you start seeing this reduction reaction occur, then maybe that is removing or destroying the polymer, or vice versa. So that's kind of my advice for starting off. I'd start with CV and maybe even do a few cycles of CV. But then when it comes to optimizing the electropolymerization process, you may find that, if I just hold a constant potential, then I form a very good coating. But I think CV would be good for initial diagnostics, at least, for understanding how to polymerize your organic species on the electrode. So, Fernando, I hope that was helpful. And I don't know if you have any other insights or comments about polymerizing organic molecules on.
I have never really.
I haven't done it.
No, I mean, well, I've done things with films. So you're talking about like a film forming and all that or whatever. I have done film formation and testing, on carbon electrodes or things like that. I have not done very, very briefly. I think when I was in the beginning of my graduate school, I might have done a small thing where there was trying to use some polypyrrole or something, some electroactive polymer. I don't even know that we were
like aniline or something.
Polyaniline, maybe.
Polyaniline?
Yeah, polypyrrole, polyaniline. There was some very short collaborative thing that we were working on with another group, and it didn't really go anywhere. It didn't last too long, to be honest. I wasn't 100%. I did a couple of things with it anyway. I didn't do enough to know. All I remember mainly from it was working with electroactive polymers is a lot harder than I thought. I guess it's quite. It can be quite tricky, I guess, at getting it to maybe polymerize in a uniform way, getting a film to form in a nice repeatable way, uniform way, where you can get repeatable results. It was a lot harder than I expected. The film technique, where you make an ink and you cast an ink onto carbon paper or a glassy carbon electrode or something of that nature, is tricky and has some difficulty with reproducibility, as a lot of experiments do, right? I'm not necessarily saying anything super shocking here, I suppose, right? But I found those to be at least easier from a practice perspective. The polymers they're just hard to work with. I don't know if it's just because they're bigger molecules or something like that, or
they are big.
Right? You're just sort of running into a lot of tricky things that happen. Fernando has a follow. I don't know if this is So you advised to do multiple CV cycles for polymerization. You're worried about depolymerizing with a countercurrent. It depends. Is it a reversible process or not? Right?
Or if the counter, if cycling back far enough does something to the electrode where it gets pushed off or something like that, or depolymerizes. So the only way to know is to do the cyclic voltammetry. So that's something. And as I said, it looks like you were advised similar thinking. Do multiple CV cycles.
Right.
And that will help you see exactly what is happening.
You can also look for, you say counter current, but like, I guess let's just say the polymerization is reduction.
Yeah.
Right. If your, let's just say, for instance, your CV, this is something where some intuition, let me know if I'm sharing or not.
Yeah, sure.
Okay. So for instance, if you're doing a CV for your electropolymerization and the polymerization is a reduction reaction, and your, I don't know, CV looks something like, this.
Mm-hmm.
Okay, well, here's my electropolymerization, but do you have any oxidation current at all? Because if you don't, that's probably not something you have to worry about, is my guess. Like, maybe if you go further, eventually you'll have, oxygen evolution reaction or other things. And then some of this positive current, like that might be bad, right? Because that could cause either oxidation and delamination of the film, or like the formation of bubbles that causes the film to delaminate. Even if you go too negative, right? That could be bad also. So my point is that to a certain extent, it's smart to consider, does the countercurrent of the other sweep, whether it's the reduction of the oxidation, does that undo the polymerization I just did? But you can even run yourself a test to see, well, okay, if I don't even see any peak, I mean, if I run it back and I do see an oxidation peak, then yeah, don't, and then it's probably not helping yourself.
Yeah.
You might be divesting the film. But if you don't have any counter current peak or very much of it, then I would say likely it's not an issue, because probably the process is relatively electrochemically irreversible, which would be in your favor.
Mhm.
That's my guess.
Yeah. Yeah. No, I think that's good. And then you can always adjust the potential window while cycling, so that you don't reach those oxidation currents when you go back.
Yeah.
Let's see.
Barry is here, and he has a very unfortunate question, which we have gotten in the past,
Mhm.
and that is, can I fix my broken platinum? So you've got, well, Pine Repair, RPG 249 PT. And I mean, everybody is so familiar with our part numbers.
Yeah.
we certainly are. So here, this is the part that I'll share with you. It's this platinum coil counter electrode. So this is a counter electrode. This is actually probably a decent explanation for in general. I mean, it's obviously specific to our company, Pine, and what we sell, but I can answer it, as a general rule as well. The short answer is unfortunately no. And the reason for that specifically with this product is that this actually isn't even an updated photo, to be honest. But at, I'm going to do a thing here real quick. So at the bottom of this, where the platinum wire comes out on our current models.
Are you drawing something?
I am, but I haven't shared yet.
Oh, okay. Just checking.
Yeah. I'm like getting it ready.
Okay.
I was doing a thing, stop
Okay.
screen sharing, and now I'm going to share. I was like doing a screenshot of it so I could draw on it.
Oh, yes. Yeah.
This one here. So all I wanted to point out was that this is the platinum counter electrode, and actually what we have in our current models is down at the bottom here. I'm drawing it in gray because I don't have white.
Yeah.
Is like a Teflon sort of plug, right?
Mm-hmm.
And so most of the time when these break, they break down here, because that's the part. This down here is the part where it's weakest. It curves, and a lot of times when people are cleaning it, it fractures right here, unfortunately. It's somewhat of a consequence. It's like platinum it bends, and then it eventually can get weaker. To try to do any kind of a solder, unfortunately, would involve heat, and you would most likely compromise this seal around this plug, this Teflon plug. And this body here, this blue, it's like an epoxy tube that could also melt. It could compromise the seal. And then the third reason, which is less specific to this product exactly, and it's something that would depend on the application, but in fixing a severed platinum strip or wire or whatever, you would do some sort of a soldering or brazing application, which usually involves another metal. A lot of times like lead, right? They make lead-free solder now too, but in my experience, it doesn't work as well. So people still do use lead, which is also an electrochemically active material. Maybe people tape it up with copper tape or silver tape, right? The problem with doing that potentially is that you're adding a different conductive material, and now your electrode is no longer a platinum wire. It is a platinum wire with something else. Now it's the counter electrode. So perhaps that's fine, because you don't generally care that deeply about the counter electrode, just that it completes the circuit, right? But that's not always the case in every situation. And of course, platinum is tremendously useful as a counter electrode because it's inert. It's a great conductor. It works quite well in those regards. If you add another material as a means of fixing it, it calls into question what might be happening at the counter electrode, its performance and things like that. It could be a little tricky for you in an unknown way. It'd be hard to sort of figure that out because the counter electrode's often overlooked and forgotten. And so, the short answer is no. Unfortunately, we don't repair those for some of the reasons I talked about. You can, of course, try yourself if you wish. To a certain extent, it's like if you want to try to fuse it back together, it's already broken. You have nothing to lose, essentially, right?
Mhm.
If you damage it further, well, you already couldn't use it, so there is that. But we can't guarantee that it would work. I can't guarantee your experiments will be great. Like I said, the quickest way is probably to you could use conductive copper tape and tape the two pieces together. If it holds, if the conductivity is still fine, and maybe you don't dip the copper part in the solution, if you can avoid, there's some possibility where that will work. I know it's tough because it's expensive, it's platinum, and so the tendency is to be pretty upset you have to purchase a new one. I am sympathetic to that. Excuse me. Of course, but unfortunately for some of those reasons, this is just a tough one, a tough pill to swallow in a lot of cases, but we can't make that repair, unfortunately.
Yeah. All right. Some people, if there's a little bit of the platinum left, some people try to tie the platinum two wires together.
Yeah.
That's another thing that if you have enough of it left,
Yeah.
it snaps at a certain part. You may have a little bit of wiggle room. You could try just tying them together. But
you get
it's
pliers,
hard.
you can twist it. Yeah, usually where it breaks, though, from what I've seen, a lot of times there's almost nothing, at the holder part of it or whatever. Yeah, so you're kind of in
that's
trouble.
maybe the only thing.
It's too bad. Yeah.
So I think the next, I'm just looking at the next.
Looks like Rajan has a question.
Rajan has a question. How to choose the amplitude of perturbation in a GEIS, I guess that's galvanostatic electrochemical impedance spectroscopy experiment of single cell, say an electrolyzer. So how do you choose the amplitude of perturbation?
So it first of all depends on the rating of your electrolyzer, right? Some are this the size, right? So if you have a single electrolyzer and it's, let's just say, a big one, like 25 square centimeter, like the fuel cell hardware, it's relatively large. You're probably, it's an electrolyzer, so you're putting in power. But if it's a fuel cell or an electrolyzer, you're looking at amps of current during operation, whether you're putting amps in or taking amps out in the case of a fuel cell. In any case, what that means is the amplitude of your galvanostatic EIS is going to be large, and it's going to feel strange because you're going to, it feels, you're used to micro and milli. I don't know. A lot of people are, at least in research labs, it's sort of, it would feel weird to do like 100 milliamp sine wave. It feels like a lot, right? But that might be necessary because effectively what you're looking for in the case of an electrolyzer is if the choice of amplitude doesn't cause the voltage to move up and down by at least, like 10 to 15 millivolts, your signal is going to be terrible. Now, part of this as well might be tricky because it depends on the potentiostat you're using. Every company's potentiostat sort of shows different things. If you're using a potentiostat that does not show you Lissajous plots, raw data at all, or you don't know how much the voltage response, for instance, moved for your given amplitude, this is going to be difficult. It's just fundamentally going to be difficult. So in that case, you're kind of blind, right? You're picking an amplitude and looking at the Nyquist and the Bode plot and hoping it's good. So if that's the case, if you can get a potentiostat and software that shows you the raw data, the Lissajous plots, anything, that would be best. If you can't, I think a decent rule of thumb where you can start is divide the, I don't even know what you would say, like the standard amount of current that your device generates or can generate or requires, like under normal operation. Like there's probably some amount of current, like, yeah, this is like 2 amps is like normal operation or whatever. Divide that by 100 and start there. That's my suggestion. So again, just for instance, if you have a 1 amp electrolyzer or 1 amp fuel cell, where that's like a common amount of current that you would put into it or pull out of it under a normal operation, right? For whatever that might mean. Divide that by 100. So that's what, 10 milliamps. So try 10 milliamps. You might have to go higher. And a lot of times what you'll see is in your Bode plot or your Nyquist plot is you have a lot of noise. And then it gets worse as you get to low frequency, because at low frequency, the impedance goes up, which means the response gets smaller, right? V is equal to IR or IZ, right? And so you're applying a set current. If the impedance goes up, sorry, I said that backwards. It's going to be worse. It's going to be worse at high frequency than at low frequency. Okay, because as you go to low frequency, the impedance goes up, which means the V response will also go up. And so as the V response goes up, your resolution of your signal gets better. Of course, it can be a problem if it's too large, but generally speaking, with galvanostatic mode, the problems are at high frequency. You get a lot of noise. So effectively, if you're looking for some decent data from like 1 kilohertz to 10 kilohertz or 100 kilohertz, and it's really noisy, you might need to increase your amplitude a little bit at a time to see if you can improve that. And as I said, maybe 100 over 100 of the sort of whatever standard current of operation might be a decent place to start. And don't worry if the data is really noisy there or bad, because you can always increase it. It's better to start too small than too big, because the worst thing you could do is just do 1 amp up and down, and the response is that the voltage goes plus and minus a huge amount. Not only because that's could be damaging to swing the voltage really, really fast in a fuel cell and an electrolyzer all over the place. That's dangerous. The second is that if you ever change the polarity of it in the wrong direction, so like for a fuel cell, that would be going from a positive voltage to a negative voltage, that could be detrimental entirely. You don't want to run the fuel cell backwards. And in an electrolyzer, it's the opposite, right? That depends how you've connected it, but you can't go on the other side of zero for a fuel cell or an electrolyzer. You could be ruining the anode or the cathode. Something bad's going to happen potentially. It could really damage things. So I hope that's decent advice for you.
He does have it's not a follow-up question, but it's just another question, which is it possible to monitor / measure the potential the counter electrode during LSV measurements using a Pine potentiostat? So unfortunately, not right now. We do have a potentiostat that we're working on that has what's known as a countersense electrode or countersense lead. But right now, all of our potentiostats, the counter electrode is just a separate counter electrode. It doesn't have a sense line for you to measure what the potential of the counter electrode is during an electrochemistry experiment. That being said, if you want to measure the counter electrode potential, you can do that. You can actually just get a digital multimeter, and maybe it's easier to just kind of draw the configuration if it's helpful. So I'm gonna use
Let
this
me make sure you're sharing.
Am I? Yeah, please let me know.
Yes, it's good. It's good. I'm going to hide the question.
Yeah. So it's hard to get the right color, but generally speaking, if I have a let's see, so you have your counter electrode is usually kind of looks like this. Your reference electrode is kind of described as like this arrow. This is kind of the circuit diagram for a potentiostat. So this is working. This is counter. Let's do CTR. And then this is ref. And this is ref. All right. So this is everything kind of connected in an electrochemical cell. But what you can do is if there's a part, what you can do is you can hook a voltmeter up between the reference and the counter electrode, and then you can just measure what the voltage is between these two. And this is actually not a bad experiment. If you want to prove this to yourself, or you can actually hook up a voltmeter between your reference and your working. So slightly smaller voltmeter. And when you do an experiment, when you say, hey, apply +1 volt, you should measure +1 volt at this multimeter to know that, like, oh, my potentiostat's working. It's actually applying +1 volt between the working and the reference electrode. So you can do the same thing. I can say, oh, let me look at the voltage across from the counter to the reference electrode. And all of these things. So maybe you have, and it should be opposite. So maybe you have like -3 volts or something like that. Oops. -3 volts, maybe. And all that's to say that you should be able to actually determine what the compliance voltage is by taking the difference. It's like, oh, there's a +4 volt difference between counter and working. So maybe you have like +4 because it's the absolute value difference between these two is 4 volts between the counter and the working. So you can hook up your voltmeter between reference and working to confirm that your potentiostat is measuring and what it's telling you is what the voltmeter is. And then you can do it between counter and reference, but you can also do it between counter and working. And you should actually discover the relationship between counter, reference, and working in a 3 electrode cell. So even though we don't have a cell cable or a lead, a counter electrode sense line to kind of measure it directly, there are ways where you can use an inexpensive voltmeter to actually measure the potential across the counter electrode. So hopefully that is helpful.
I want to add one bit of clarification
Mhm.
because I was looking through some records, some emails and tests that I had done like 3 or 4 years ago. Just to clarify, everything you said is correct. We don't have a counter sense line on any of our potentiostats. There is, however, a way you can practically measure the potential of the counter electrode only if you have a bipotentiostat.
Oh yeah.
It is actually possible. It's not necessarily intuitive. It's a little tricky, but it can be done. So if you have a wave driver 200 or a wave driver 40, for instance, bipotentiostat, you can. What you have to do, I'll just describe it briefly, and then Rajan, you can reach out to me. I think I've emailed with you before. I think I if you're at IIT Bombay, if you're the same Rajan who's there, you basically connect your experiment like normal, and then the blue and the purple lead on your bipotentiostat cell cable, the second working electrode, you would connect that to the counter electrode. And then it's a software thing. So you would have to run a software experiment, and it's not LSV. You'd have to run like it's one of a number of methods. Like you'd have to run like dual electrode methods, you dual electrode like voltammetry, something like that. And you would set the second electrode. You have to pick a certain mode. Anyway, the point is that you set the second electrode. The simplest way to do this, I know it sounds strange, is have the working electrode one, like the main one, it's a voltammetry, and do your LSV or CV, whatever, and set the working 2 electrode K2, the second one, to galvanostatic mode with current equal to 0. So that's basically OCP, right? It's in a galvanist. It's measuring the potential with no current. It's just passive. It's doing nothing basically, but it's measuring the potential, and it will be measuring the potential at the counter electrode since you've connected that lead to the counter against the reference. So you will get those measurements. But again, it only works if you have a bipot, and it's not going to be labeled in the software. Counter electrode potential. It will look like the second working electrode, or So, but it is. I think it is technically possible. If you need more help getting that set up, you can reach out to me separately. But again, yeah. So you got the point. Okay, great.
Interesting. All right. Follow-up question from Lingesh. The diffusion layer grows because the product formed or reduced species extends the layer and it decreases the mass transport? Question mark.
So it increases the mass transport.
What does that mean?
Well, he's saying diffusion layer grows because the product formed or reduced species extends the layer and it decreases the mass transport. You know what? Actually, that's a good question. I don't know why the diffusion layer grows. I just know that it does.
Well,
do you have an explanation for that?
Yeah. So the diffusion layer is just the it's the layer of the. Let's see if you're doing. Let's see if I'll. Let me share my screen just to kind of make it.
I don't know if I can.
Let me share first and then. Okay, so if I have my electrodes, if I have my electrode surface. Wait a minute. Hold on. I have a presentation where I've done this before.
Oh, well, look at that.
So let me
track it
get
down.
that. Hold on, that wrong one. And then I think it's electrochemistry lecture. Okay, so let me share my screen again and get to the slide. So can you? All right.
Yeah, you're good.
It's for Houston. Okay. So this is how I think about diffusion. This was diffusion from a for like a potential step experiment, like chronoamperometry. So this is the case where you have your electrode, and all these little orange circles are your analyte. They're the thing that's going to get oxidized. So and then in the upper right hand corner, this is just potential versus time. And I have a little arrow or a little dashed line to say at what time what's happening. And so I can do this for cyclical voltammetry, but we can do it. I can do it twice if you want. So at this point in the chronoamp experiment, the electropotential is positive, and everything here, this is the diffusion layer, the molecules that are immediately adjacent to the electrode surface will get oxidized. And then as time goes on, time is going on, some of these orange molecules will get a little bit closer because they're randomly diffusing around, and they'll get closer to the electrode surface, and they'll start to get oxidized. So you have more of that. And so as time goes on, this diffusion layer starts to thicken and extend because these little orange guys are randomly making their way towards the electrode surface. So this is why the diffusion layer keeps growing. It keeps growing because all of these little, it takes longer for like a little orange circle to be, the orange circles here outside of the diffusion layer represent the bulk solution. So the bulk solution looks different than the solution next to the electrode surface. The actual species are different. There's a few of these little orange guys, but it's mostly these red oxidized species. So that's why the diffusion layer starts to increase over time. It's because it takes, because more of these molecules are becoming oxidized over time, and it just keeps growing, and it just takes longer and longer for one of these guys to make it all the way towards the electrode surface. I have another visualization of this for cyclic voltammetry. So if you look at in a CV, this is the waveform, and as you kind of continue, this is for a reduction reaction. You start to generate your diffusion layer as you're reducing species, and then your diffusion layer keeps kind of increasing, and then as you're going backwards. So this is actually the same potential between these two slides. Sorry, between this slide and this slide. The diffusion layer increased. Sorry, I'm making it very confusing. The diffusion layer increased because you're at this potential longer. You're at the top part of this. And then as you go, it's like, okay, well, then the diffusion layer starts to change a bit because this is now less negative, not negative enough to convert this guy, to reduce this guy. And then you have this guy. And then by the end of your voltammogram, you have a very kind of mixed diffusion. There's some of your reduced species here, some oxidized here. But that's why it increases. I think the chronoamp kind of describes it better, why it grows over time. So hopefully that helps with understanding why does the diffusion layer increase with distance over time for
Kind of feels
for
like,
these
based on your
experiments.
like the cartoon in your slides.
Mhm.
I don't know. Tell me if this is a decent, how exactly how perfectly accurate it is. I don't know, but it's kind of like as you turn the orange to red,
Yeah.
there's more red, and so the diffusion layer is kind of like not exactly. Take it for what it's worth,
Mhm.
but it's like the distance from the electrode surface to the next available orange.
Yeah,
Kind of.
kind of.
Obviously not exactly precisely, but in some ways it's like that because diffusion is randomly moving them around. And
Mhm.
so as they start to turn red, you're looking for orange because
Yeah.
orange is the thing
That's
that's going to react. And it's like,
yeah.
if it's close, it's good. It's easy. It's going to do its thing.
Yeah.
Give you a lot of current. If it's really far away, it's going to take longer for
It's
it to
gonna take
randomly make
longer.
its. And as there's less and less orange nearby, the distance to get from the surface to the next available orange just keeps getting farther away.
Yeah, it's
Something like that.
yeah, it's something like that.
That's kind of what I was looking for when I was saying, like, I don't know how to describe it, but
Yeah.
that cartoon I think does a good job.
Yeah. It's also important to note that you're measuring the current, which is the rate of the process.
Yeah.
So when there's lots and lots of orange around to convert to get oxidized or reduced to red, the rate's really fast. But as the diffusion layer grows, the rate with which a new orange can make it to the electrode surface starts to slow down because they're all moving at the same speed. Like it's not like an orange from away from the electrode surface is just like, oh man, like there's so many red guys here. I need to make it to the electrode surface so I can be red. It's like, nope, it's just moving around randomly. It's just it requires an orange to randomly make it to the electrode to get reduced or oxidized, and yeah, as you form that layer, it just takes longer and the rate decreases. So hopefully that gives him a little bit of a physical idea of the diffusion layer. Lingesh. Okay.
Yeah, Barry's saying that the platinum broke right at the base. That's
Yeah.
unfortunate. Yeah. So
Yeah. Super.
yeah, it is soft.
Yeah,
it's
very
unfortunate.
soft.
You just got to be really careful. Unfortunately, there's not much more that can be said. I know it's not much of a consolation, but yeah.
Sorry.
Bahram says, when we have a Warburg response at low frequency of an EIS spectra of a corroding, I assume that's aluminum.
I think so.
Yeah, I assume it's not AI. Like it's a corroding artificial intelligence.
Corroding artificial intelligence.
It's AI that's just progressively giving you dumber and dumber answers.
And it generates a Warburg short somehow.
It does. That doesn't sound very dumb to me. It sounds like a smart AI. Anyway, I assume it's aluminum. We usually use a short Warburg, right? Okay. Does that imply the diffusion limitation happens within the oxide layer on the aluminum? Probably. Or at most a very small, and I mean probably, I don't know, tens to hundreds of microns small, not much bigger than that. Like layer, we just talked about diffusion layer, something
Yeah.
like that, right at the edge of the surface that does not extend any deeper into the solution, right? Because otherwise you would have an infinite Warburg, and the EIS spectra would reflect that. Okay, so I think that whether it is within the oxide layer or not is probably a little difficult to determine. But you might be able to try to independently verify, for instance, by taking the Warburg constant you get from the Warburg short, and or it's the other constant, actually, really, to be honest. It's like the B. We call it B in our software. I don't know. It might be called something different in other software circuit fitting programs that you use. But if a Warburg short has two circuit fitting parameters you get out of it, right? One of them is the Warburg constant, and the other is some other thing. We call it B, again, whatever you get it. But it is equivalent to what is it? The square root of D over the diffusion layer thickness, or something like that. But effectively, that B is proportionate to the diffusion layer thickness. And so you can, in some way, quantify the diffusion layer thickness, the thickness of the Warburg short. And so, just as a suggestion, one thing you can try to do, for instance, is if you suspect, hey, this is the corrosion taking place in the oxide layer, is extract from your circuit fit and calculate as best you can a measure of the diffusion layer thickness from the Warburg short circuit fit. And then if you have some sort of physical, spectroscopic, microscopic technique, SEM, I don't know, some kind of spectroscopy where you can probe the surface to get a physical measurement of the oxide layer thickness, maybe that's not possible. So this might not exactly be easy, but if there is a way for you, or in the literature, for instance, if you find someone who did determine the average thickness of your oxide layer, for instance, you could compare the two, is my point. Because you might, let's say you do the Warburg short and you determine that it is roughly 1 micron, right? But or 100 microns, let's say, from Warburg short, but you do a literature study and you find that, like, the oxide layer is no thicker than a nanometer. I'm just making up numbers, right? But it's like, well, those are so far off, maybe that's not a proper explanation. Okay, so perhaps it's something else. But if you find that those are within an order of magnitude, let's just say, then that might be somewhat of a confirmation of your theory. But I do think that that's a good theory. I think you're thinking the right way based on your interpretation of your Warburg short results.
All right. Akashdeep says, "Hi, can specific capacitance increase with increase in current density? If yes, kindly explain the reason with reference. Thank you in advance." Well, I don't really know enough about specific capacitance. I believe it's the capacitance per mass.
Area or mass?
Yeah, just a quick search just said it was like specific capacitance is in units of farads per gram.
Okay, so it's mass based.
So I think it's mass based. And current density is current per area. So can the capacitance increase with?
This just seems like equation math.
It feels like it without a system.
Like right. I is equal to C times C is equal to, like, capacitance, right? Not specific, just capacitance itself is equal to, for example, if you're doing a sweep, current times scan rate.
Yeah.
So if current or current density, either way, goes up, capacitance goes up.
Yeah.
So if current density goes up, capacity still goes up,
Goes up.
right? And They're
Yeah.
they're proportional, right?
Yeah.
Current is directly proportionate to capacitance,
Yes.
not
Yeah.
capacity, capacitance.
Yeah.
And so specific capacitance is just taking that number and dividing by however many grams of stuff you have. So it's
I
still
think
going
so.
up.
Yeah.
I mean, did I think that through right? Like to me, it's like this. There might be a deeper question that he's asking that I'm not understanding, but effectively, it's like forget about specific capacitance and forget
Yeah.
about current density.
Yeah.
If you just take,
Because they're normalized.
yeah, exactly. It's like you're normalizing to area or to mass,
Mass.
but effectively, if the question is, does capacitance increase when current increases? The answer is yes. The measured capacitance increases as your current
Yeah.
goes up.
Yeah.
That's just true, right?
Yeah. I mean, unless unless like your scan, like if it's a CV experiment, like if your scanned rate is increasing, then your capacitance can remain the same while
Mhm.
your current goes up.
Right.
But that's just kind of like manipulating the numbers a little bit.
Yeah.
But if you have like if you're studying a system and you have the same experimental parameters and you're just like, oh, I changed a thing with my system and I get more current,
Yeah, it means you have more capacitance.
I probably have higher capacitance then.
Yeah.
So that's So we don't have a we have a reason. We don't have a reference per se. We just use
Yeah.
some math.
Just looking at the relationship of the equations relating capacitance and current.
Yeah.
But yeah, I mean, if that's what you're observing, that is what it means. The fact that one is in density and one is specific, I suppose, right? It's
Yeah.
somewhat inconsequential unless you have a question related to like if there's a deeper experimental detail, like I'm changing the mass and I'm changing the area and I'm doing all these other different things. And what's
Yeah.
the correlation between all those things? That's a bit of a more complex scenario, right?
Yeah.
Which we could probably theorize through, but usually in all articles, specific capacitance decreases with increasing current density. So again, the hard thing that I'm trying to wrap around here is that one of them is specific to mass and one is specific to area.
Yeah.
And it's just the only thing that I can think that comes to mind is, you're dealing with two quantities going in opposite directions or whatever, right?
Yeah.
But they're with respect to different physical properties of your material, which is to say
Yeah.
one is related to mass and one is related to area, right? And
Yeah.
mass and area are related to each other. Like, for example,
Via density.
right. Well, mass and volume, and then area.
Yeah, and then
area related to its geometry.
Yeah,
right? So
its
like
geometry.
we're getting into the realm of physical characteristics of your material. And so what
Yeah.
I'm guessing is when you're observing this phenomenon, it has something to do with the physical characteristics of the material. And so, for instance, if current density, I'm going to talk through this and maybe I'll come somewhere and maybe I won't make any sense, but I'm going to try. If current density is increasing, current density is current over area. So if area decreases, but it's in the denominator. So one explanation for current density increasing is area decreases, right? Because it's in the denominator. So if area is going down, okay, the current density would increase. So why would the area be going down? Is it might be you could have, for instance, okay, and then conversely, specific capacitance is decreasing. So that suggests if specific capacitance, which is capacity divided by mass.
Yeah.
So that means that mass is going up, capacity goes down. So this is my guess based on the information that I'm working with that you've given, which without reading papers and kind of thinking this through or studying this through, this is what I think would be an explanation. You're increasing the mass, which means specific capacity goes down, capacitance goes down, increasing the mass, but you're decreasing the surface area, which means the current density goes up, right? They're going in opposite directions. And the reason for that is that as you increase the mass, it's like adding more material. you're loading your film, you're loading your working electrode with more and more material. Often that means the area does decrease because you have agglomeration of material. So if you have like nanoparticles of platinum, for instance, this is a phenomenon that is observed regularly. If you have nanoparticles of platinum, the best way to access them is to use a very small amount of mass because they're very small. You can think of them as very small orbs or balls. Okay. And if you have one here and one here and one here and one here, they're sitting on a substrate of carbon or something like that. And all around this orb of platinum, all around it is accessible. It's got a huge amount of surface area, right? I can have a molecule come over here, a molecule come over here, a molecule come over here, and great. It's super a lot of surface area, right? A sphere is right geometrically. A sphere has the most the highest ratio of surface area to volume or whatever, right? It's like minimized, right? Or maximized.
Mhm.
So that's why people go for nanoparticles. The smaller the spheres. Now, if I increase the mass, now they're all butting up against each other. They're all next to each other, right? Well, now two spheres that are next to each other, I can't get into the space in between the two. I'm losing surface area. And what if the materials start to grow together and they make a big giant orb? They grow and they coalesce. It's called Oswald ripening. They get bigger.
Hmm.
So I have a big sphere. I've increased my mass, but I've actually decreased the surface area because now my material is glomming on together and I have less available area than if I just had individual orbs all happy and separate. Okay. So my guess is that would explain the phenomenon that you're seeing. Again, as the mass this is not always the case for every material in all situations, but in some situations, as the mass increases over some range, the surface area decreases because the material is no longer accessible everywhere, and it agglomerates. The particle sizes grow, the grain boundaries grow, and that decreases your effective surface area. And so this is why people try to, for academic purposes, decrease the loading sometimes, decrease the surface area and the size of the material and the molecules, because you'll get more activity and more surface area. So I hope that's clear. I think that might be the explanation for what you're seeing.
Yeah, I have to think about it. I just like I can't keep track of like one thing goes up, one thing goes down. When this thing goes up, this thing goes down.
Mhm.
This thing goes up. If I have a small this, I have a bigger that. I'm like, oh wait, and we're trying to demonstrate which one's going up, which one's going down. I'd have to think about it more to wrap my head around it. But yeah, I think anyway, I digress.
Mhm.
We have a question from FCB. FCB asks, it has two parts. Can CV confirm the oxidation state of a catalytic reaction? And then he also asks, can we stop mass transfer to analyze organic synthesis reactions by electrochemistry? So the first one, can CV confirm the oxidation state of a catalytic reaction? Well, um, I'm gonna say no. You can oxidize and reduce things, but it's not like it tells you, oh, it's +1 to +2, or +3 to +4, or plus whatever, or minus whatever. It doesn't actually tell you the information about the oxidation state itself. You would have to look at the potential with which that oxidation reaction is occurring, and then sometimes people usually look it up in a book, or they know something about their starting material, to say like, oh, this copper is in the +3 oxidation state. For this is, I guess, a homogeneous. Let's say if it was a homogeneous reaction, and we had a homogeneous catalyst, it was you had to know it was in the +3 oxidation state when you put it into the system. And then from there with CV, if you say reduce it to the +2 oxidation state, you should be able to see that. So you could see the +2 oxidation state being formed. but you wouldn't know that it's +2 unless you knew ahead of time that you were putting like +3 into the system. I also so that is assuming you have like a molecule, but you're saying the oxidation state of a catalytic reaction. So the oxidation state is usually something that will assign to a molecule, not to a reaction itself. So I would just keep that in mind. But that is, but yeah, if you're talking about can it confirm an oxidation state, it's confirm. So if you had other tools to help you, and you say looked at the voltage again, if you looked at the voltage at where this reaction was occurring in CV, you could then probably look at like a book with tables of potentials and be like, oh yeah, this redox state is approximately where we would normally see it based on this table of oxidation reduction reactions and potentials. So that's the only way you can do it. But a CV by itself doesn't just tell you it's +1, +2, or +3 or something. Now, FCB asks, can we stop mass transfer to analyze organic synthesis reactions by electrochemistry? I don't know enough about what you mean by stop mass transfer. There are in electrochemistry there are these three forms of mass transfer: diffusion, convection, and migration. Convection and migration are ones that we have a little bit more control over by like stopping it, but it's hard to stop diffusion, sort of say. Diffusion just happens. Stopping random Brownian motion um, is difficult to do. But if you're in the middle of an organic synthesis reaction, people do remove aliquots of their organic synthesis reaction, and then put it into an electrochemical cell and then analyze it. And they would analyze it under the conditions of diffusion. So to do that, they would add a supporting electrolyte of sufficient concentration to remove migration, which is mass transport associated with an electric field. And then, if as long as the reaction vessel is sitting still, you're not stirring with a stir bar or anything. If it's still, then you've removed convection, which is kind of the macroscopic movement of molecules. So that is what you can do. I hope that makes sense. It's a little hard based on the way you've worded the question, but based on what you're describing, I hope that what I said was helpful. If you're trying to analyze organic synthesis reactions with electrochemistry, you can't stop you can't stop all mass transfer, but you can minimize the effects of migration and convection, which is helpful. Let's see. So again, and for everybody who's asked questions, please give us a follow-up question if something we said didn't make any sense. But moving forward, Gultekin, I'm sorry if I'm mispronouncing anyone's name, asks, can you suggest the best setup and method to measure ionic conductivity of an ionically conductive membrane, PEM? In the literature, many discrepancies about EIS. Some fit to a typical Randles cell, but is I guess tether a
No, is there
an
RCT?
an RCT
Yeah.
there? I guess, well, if I don't know exactly what the system is, I can't actually say. But I'm assuming you're thinking about the discrepancies in EIS for measuring the conductivity, or specifically the impedance of a membrane. He has PEM, so I'm assuming it's a proton exchange membrane that you're trying to study. So one thing to keep in mind is what one thing I've even learned is RCT will show up if you have a redox active molecule and you're doing EIS at the potential to with which that redox reaction is occurring. Otherwise, in a way, your circuit will look different or behave differently. But I think EIS is really I don't know. I would say EIS is probably one of the best ways of what we know to measure ionic conductivity. I think the cell that you use will play an important role. I think a lot of people use an H cell, some type of separated H cell, where you have your membrane. Sometimes you have like a working electrode and a reference electrode, or two reference electrodes, like across from each other in between the membrane to measure conductivity. But I honestly haven't done too many measurements of the conductivity for a membrane, for a proton exchange membrane.
I have a
So
little diagram I can show.
you have a diagram.
I'm just pulling it up right now. I can
Mhm.
find it. Try to find the most recent iteration of this. Siemens. Yeah. So let me get it somewhere here really quickly. I'll kind of try to
Oh,
describe this through.
yeah, and we have a follow up. Just kind of, yes, it's a proton exchange membrane in a 4-probe experiment, 4P setup. So I think it's
Okay.
just a 4-point
Yeah.
probe.
So what I'm showing you is similar to that. Okay. So I'll share my screen here. This one. So the setup is something like this. Might be something like this.
Mhm.
So you'll have, I know this is kind of off the screen here. I'll try to make it a little smaller so you can see. So you have two reference electrodes on either side, and then two, like, usually just platinum coil, any sort of working electrode. And basically this is like a cross section of this. You have the membrane in the middle. You can't probably see it here, but basically there's a membrane in the middle. There's two long Lugan capillaries that go right all the way to the middle. And the reference electrodes are in those, and there's solution there. So the first thing about the EIS and the RCT thing is that, as Alex said, it kind of depends. You generally are trying to measure the conductivity of your membrane. You don't want to have a faradaic reaction there. So there's definitely a lot of discrepancy in EIS. I don't know if you would want to use a Randles element for your fit, to be honest, because that implies a charge transfer resistance, which implies a faradaic reaction, and you probably don't want to have a faradaic reaction going on. You want to have everything, like you just use like plain salt solution, or if it's a Nafion membrane, like plain sulfuric acid, like 0.1 molar sulfuric acid with nothing else. You don't want to do oxygen reduction. You don't do oxygen evolution, hydrogen. You don't want to just do a neutral potential where you don't have anything in particular of interest happening. And what you're doing is effectively, this is like the cross section here. So you have your Lugan tube. You want to get an estimate of the distance between the two Lugan tube openings, and you have your Nafion in between, and there's solution everywhere, like sulfuric acid, right? And so the ways that this is in theory done is one of two ways. One of them is you can run, like this is from like an email I've sent to people before, right? Is you can run a short LSV experiment. This is something like linear polarization resistance. And so around OCP, you just go 100 millivolts or 200, 300 millivolts up and down. It hopefully makes a straight line. And then from the slope of that, you get the resistance. Or you do an EIS. And probably somewhere at the high frequency range, you would get the ohmic resistance, and that would be it. I don't know, in theory, I guess that's the thing too. It's like, this is a tricky thing. So if your impedance measurement, I guess in theory, would just look like this for the Nyquist plot, right? Minus ZI and Z real. And so you're just looking for this point right here. That would be your R. Just the intersection of the axis here. If somehow you have that, I don't know what this is your RCT. Maybe that's what you're getting, and I don't know what that faradaic reaction is, or maybe that this RCT here, maybe if that's what you're getting for some reason, that is the resistance of the membrane. I don't know if that's what you'd expect. I haven't done this experiment myself personally. I just sort of speaking from a theoretical point of view here. But if that's what you get, the red curve, then maybe that is what you're looking for, and you would fit this with something like,
That's interesting. He's making a comment. There's no solution, just the membrane in a humid environment.
in a humid environment, just
Yeah.
the membrane.
And he says, I have just read a number of papers just on this subject, so no standard method. Interesting.
You can't really do this in just a humid environment, or you can, but your results are going to be ridiculous because you're basically getting effectively okay, if so forget about this diagram here.
Forget about this whole thing. It
If
doesn't
instead
work.
what you have is a situation like this, you have your Nafion membrane laying flat on a table, and you have probe, like touching the membrane, right? And this is like reference, this is working sense, this is counter, and this would be working drive. Then L, the distance, is this distance here between your two sense lines, and you just have the probes touching the membrane directly, and the membrane itself is like soaked in sulfuric acid. So I know it said no solution, so it's not like a liquid system, but it's like a wet membrane. There has to be electrolyte. Like you can't do this, in my estimation, with like no electrolyte whatsoever. I don't think it's like physically possible, because if you do impedance on an open system, you're just getting the open air leads. Like that will dominate your experiment. The capacitance of open air, of the open leads, is like so incredibly small that its impedance dominates your results. You have to have some solutions somewhere. But the mathematics of it is that you're trying to get this resistance, and basically conductivity is this equation right here. It's L over RA. So you have a surface area of your membrane, right? Whatever the surface area is, I guess. And then the L, the distance between your sense probes, and the resistance you measure, right? And when you do that, you get Siemens per centimeter. So that's kind of what I can tell you about that. Again, I know.
Yeah, he's saying that they don't use electrolyte in the literature.
Yeah, it's just.
I guess we just don't know what's happening then.
Between point wires. Yeah, there's if anything works with something like that, it's impedance, because impedance is like a weird experiment where you can kind of get away with having DC methods would never work. But take the high frequency resistance. That could be it, is the high frequency resistance is what you're doing for the R, and then it's the L over RA, like you just said. That might be it. I'm very skeptical. I mean, you might be right. I'm sure there's a lot of literature there, but maybe there's something like, is the membrane soaked or something like that? Like you're doing electrochemistry, like charge is moving somewhere. It's electrochemistry. Like it has to be. That's just like how potentiostat works. That's how electrochemistry works. Charge is moving somehow, somewhere. And charge doesn't move through the air unless there's a lightning storm. Like there's just some charge is moving somehow, right? There have to be ions in the membrane moving. It has to have been soaked somehow in electrolyte. Like something is there that is missing from your description. I just feel like it has to be. There's just no way that you just have like just some, like, you can't just take some piece of paper from a textbook and just like take probes on it from a potentiostat and just do impedance. You'll get nothing. There's no conductivity. There's nothing,
Yeah, if it's not,
right? Like,
yeah, if it was a piece of metal, it'd be a different
yeah,
story.
right. It has
It has
conductivity,
connectivity.
but just, so something is somewhat missing from this understanding for me. I'm talking
Yeah.
about, but generally speaking, that can be done, for sure. Like this whole probe, just plopping them on a thing on flat on, that can be done.
Yeah.
But yeah, good luck with that, I guess. In that instance, probably the high frequencies.
Mm.
I don't know what you're looking for, but yeah, that's the best that I can, I don't know, think in that situation for you.
Yeah. Okay. If we scroll back up, because we had a good text conversation. I don't know. Do we so Aksheptit is talking a little bit more about like current density and specific capacitance.
Yeah.
Specifically looking a little bit more at the units. And the idea that current density also can be presented as amps per gram, and specific capacitance can be looked at as current per
Yeah.
distance.
So you're basically, so this might be literature that I'm not familiar with either. So there's part of this, admittedly. Current density traditionally and typically and most commonly in electrochemistry is current per area, not per gram. But but you can,
Yeah.
but in your situation or case, the density or the specific part of that, right? Specific in density as like words related to units just almost always means it's divided by area or mass, like one or the other, right? Usually density means area, like, or volume. It's a length thing, and specific usually means mass. In your case, maybe that's not the situation, but you did say this. So again, I talked through the possibility. I still think it's might be the case. It's just that, there's this sort of odd divergence of available area as mass increases. And even if you're not talking about current density in a typical form related to area, but you are mass, the point of it might still be the same, which is that you have a phenomenon that's somewhat counterintuitive, which is that generally speaking, for a lot of systems, as you increase the mass, it does not always correlate to a commensurate increase in the performance or the current, because the available material is not getting bigger. Or it kind of does a curve thing, like increase the mass, you're adding active material, the performance starts to go up. And then as you keep increasing the mass, the performance will drop off a cliff, because it's no longer, you're adding mass, but you're decreasing the amount of like available stuff. So something like that might be at play. The only other thing I can say, you basically made this, you're talking through the equations also, right? So current density, as you've described it, is amps per gram. So this is part of it. And basically, if you just do this math effectively, it's like delta T and delta V. So you said times the time and over the voltage, the change in the voltage, right? Just unit wise, amps times seconds, that's coulombs, right? And then volts is down here. So coulomb per volt is a farad, and it's divided by grams. So that gives you coulombs. Excuse me, not coulombs, farads.
Farads per gram.
Yeah, exactly. Thank you.
Yeah.
So the capacitance. So the specific capacitance, or that whatever the capacitance density, whatever the word is you use, is farads per gram, and you get there by this just dimensionally taking the current density or the specific current, whatever you're calling it, times delta T over. So another way to just again think this through dimensionally without any other phenomena, like I tried to explain with the mass of the thing changing and the whatever current that I just talked about, is that if this is going up, but this is going down, excuse me, then it has probably something to do with these two quantities somehow, right? If this goes up, this should go up because these are directly like related. But perhaps the delta T is very small or the delta V is very big. I don't know how else to describe this. Like,
Yeah.
right?
So-
Like just dimensionally, if your voltage change is really big
Mhm.
over a very short period of time, even though your current goes up, then your capacitance will be lower. Something like
Yeah.
that.
I would also make the comment just something. So you're saying that you see these in lots of articles, lots of different articles. And so one thing that I have observed is I don't really talk I feel like I don't hear too many people talk about current density when they're talking about capacitance. Like they're always talking about some kind of reaction or what a fuel cell is producing or something like that. Like I think we really need to know like what is the article, because I think there are other factors at play that we just don't know about, and all we have is just this dimensional analysis. We don't know anything else um, about the article and the systems that they're talking about, because I think uh, actually you have a good a good point. Like it's kind of weird, like what's happening. Well, when you have nanoparticles, things are different. When you have just macroscopic things are different. When you have things of different, we need to know also what the units are. Like we thought it was current density was amps per square centimeter, but it turns out it's more like amps per gram. Well, I think we just have to see what it is to really like nail it down. I think this requires a little bit of knowledge. Like, send us an example article or two where you observe this phenomena, and you might find that like it's just maybe there's a subtle misinterpretation of like the graph or the data, because current density, I don't know, some people might say like, all right, well, current density might be due to a faradaic reaction. Well, if faradaic reactions are occurring, then your apparent capacitance might be decreasing. Who knows?
Yeah.
But we have
'Cause
no
some
clue.
of the current is divested into a
Yeah,
different process or whatever. So
yeah,
there's a
it
lot of
could
other
be
stuff.
something like that. So it's hard to tell right now, just based on this analysis with the units, like why something may or may not happen. So we apologize for that.
Yeah. Hopefully some of what I tried to
Yeah.
explain to you might cover an explanation for what you're seeing. I think something might be there, but I obviously can't be totally sure, like Alex said. So
Yeah. Lingesh is asking, can you please explain about SECM and its principle, and also spectroscopy and microscope techniques are using electrochemical studies? Is that field is narrow? How to start work on that, and where to begin? Um, so SECM is scanning electrochemical microscopy. It's an imaging technique, like real, very kind of simply. I was just trying to look at the units and thinking about the mass of all that stuff. But in principle, for SECM, you have a two electrode. You kind of need a bipotentiostat to do this, but you have one electrode that's like a tip. It's a needle. And then that's kind of in maybe kind of a reservoir with another thing. I'm going to delete this. Let me just give it a little bit more space. So I'm going to get this a little bit lower. And then I have my electrode down here. Make sure I'm showing everything right. So this is another electrode. This is my surface. So this is my working one electrode, working one, and this is working two. Okay, and then this is all in some solution, as it always is, right? So that's in some kind of solution, and there is and let's just put it just over here off to the side. There's a reference, and then there's a counter. Okay, so there's a counter, there's a reference, and so it's It's like a 4 electrochemical system because you have, you basically need a bipotentiostat to work this. So what happens is this all needs to be connected. This platform is connected to a piezoelectric device. So I don't know how to visually represent it, but it's like I'll just call it piezoelectric device that allows you to move the surface very, very slowly and by nanometers, fractions of nanometers in position. And what happens is when this is connected to a potentiostat, you add what's known as a redox mediator. So this is just something very simple. Ox plus red goes to plus electron goes to red, reduced. So you put a very easy to oxidize and reduce molecule in this system. And what happens is if I were to blow this up, and it looks a little bit like this. This is the tip. And this is the surface of my electrode. There will be a certain point where you hold the potential of your working one such that, let's say you hold it such that ox becomes red. So this is a very negative potential. So any OX that's here immediately gets reduced to red. And then similarly, we hold this potential, working 2, sufficiently positive. This is very positive. This is very negative. Sufficiently positive that any red immediately turns into ox. And so you have this redox mediator that's constantly cycling. And this constant cycling only occurs if the distance here is like 1 diffusion length or something like that, nanometers in distance. So this only happens on like the fractions or point nanometer. This looks like a millimeter. Nanometer kind of distance. So that is why, and this is based on distance. So this always happens. And so if this surface, if this working to surface, instead of it being flat, if it's jaggy, if it's got hills, if it's got an active site, if it's got a redox site, that's really cool. You will constantly scan this with your piezoelectric device. It moves around because it's trying to maintain a special current that is between the working and this is working 2, between these 2 electrodes. It'll maintain this kind of feedback current. That's what we call it, feedback current, I believe, to maintain this distance as it moves up and down and not raster scans, but just scans across the surface of your working 2 electrode. And what's cool about SECM is that when you do get these active sites, you all of a sudden get some like, oh, that looks like a happy face, or a surprised sad face. You get this kind of active site can be shown in the SECM. So this is a microscopy technique for imaging, but people use it to show catalytic activity because you'll get an extra bit of current in addition to just the redox feedback current. That is the fundamental principle behind how SECM works. And let me just make sure that there's no kind of like follow-up on that. So that's the principle. There are many other techniques out there that have to do with microscopy and spectroscopy. A lot of spectro-electrochemistry experiments just involve having your working electrode. I'll just kind of put the working electrode, describe it like this. So this is my working electrode in an electrochemical cell, and I just shoot laser at it, and then so that's like spectroscopy. You shoot the laser, and then you look at the scattered light, or the backscattered light that happens when you have some kind of oxidized or reduced species on the surface. That's the general principle behind spectroscopy or spectro-electrochemistry. And microscopy is kind of the same thing, except with microscopy. So microscopy like SECM is one thing, but there's also literally just like, again, if you have an electrode that looks like this, you can just take pictures. You can just like take pictures with a camera. And I can't draw a camera, but it's like, you're taking pictures, images of what's happening on the electrode surface in real time, and you get a camera that's fast enough to capture things on like the milli or microsecond time scale. You can start to image how the electrode changes with high current or low current or in different electrolytes, morphology changes. So that's an imaging, I would say, as opposed to a microscopy. But it's an image. You are getting an image of the electrode. But a lot of these are like, we take we get an electrode, we have a special electrochemical cell, and then we couple it to our laser or our microscope, such that the other instrument, like the spectrometer or the light source, works in tandem with the right timing of the potential that you apply to the electrode. And that's kind of how these things, generally speaking, work. I think SECM is probably the more interesting one, but it's just there are people who are doing fundamental research in expanding the technique. There are people who are just using the technique. We offer a UV Vis spectro-electrochemistry bundle. So the spectrometer, light source, electrodes, and potentiostat all together, are purchased, and they're used to study electrochemical processes where there's a change in the color of the molecule, or the change in the molecule color is actually in the UV instead of the visible. But if there was a how to get started, I would start with UV Vis Spec Echem, because it's the most kind of well studied in a way, and there's a lot of off the shelf. I just mentioned a thing that's off the shelf solution, but I would find a lab that's doing spectroelectrochemistry or uses spectroelectrochemistry as a tool. So Lagesh, that was a lot, but let me know if you have any general questions. But yeah, hopefully that was helpful.
I'm glad you explained that, because I didn't have a lot of knowledge of SECM.
Yeah, my research group in grad school was starting to do SECM towards the end of my time there, so I ended up like reading a lot about it.
Yeah.
Not actually doing it, because
I have never done it.
we didn't buy an SECM. My boss wanted to build one from scratch, and it's just like,
It's probably really hard to get that like calibrated right, because the distances are so small and everything.
yeah, these piezoelectric devices are really pretty good nowadays. The technology is very good. Everyone does like AF. It's the same like,
yeah, it's
you just buy
AFM with electrochemistry.
Exactly.
You're not actually touching it,
yeah,
right?
yeah,
Which
you're
is the
just-
benefit, that you're not maybe damaging the surface or scratching it or whatever.
Yeah.
Because AFM necessarily like touches the surface.
Yes. Yeah. And but you always have to add a redox mediator. So
Yeah,
So
it's
it's
gotta-
like if I want to study something else, it's a little hard. But yeah, it's a
That's
thing.
cool.
Anyway.
Sudeepta has a question. I'm currently working on OER. I faced issues during the calculation of specific capacitance. When I perform CV in non-faradaic regions, start and end point does not align. Can you help? So I guess I'm not 100% sure what you mean. I'm going to try to just illustrate something in our software, because I can simulate this for you. But I guess the main thing is what is the problem? Like the start and end doesn't align. I don't know what you mean. Like if you're doing a determination of capacitance through a non-faradaic sweep, you'll have positive current on one side and negative current on the other. They're not going to align. Like they're not. It makes like a rectangle, right? I mean, that's what happens. I'll kind of illustrate that for you. So this is just, for example, a cyclic voltammetry of a 1 electron process. So here's like, okay, great. Here's my E, 1 electron centered around 0. Okay, so what I'm going to do to sort of simulate something here is I'm going to move this E 0 to like 1200. Okay, and I'll simulate this again. So I'm just pushing. I'm like, no, sorry, I want to go the other way because of the way the simulation kind of does this thing. I'm gonna go minus 1200. So, okay. So don't worry so much about what this looks like. The point is like, okay, now my E0 is way negatively, so I'm barely getting to the redox. This is like doing a scan in a non-faradaic window or something like that, right? And so just to be sure, I'm gonna like only go down to 0, and my redox is at minus 1200. So this is like almost no current, right? So this is basically just flat. Now what I'm going to do is wait, this note is telling, okay, I can't get to I couldn't get to it because the height. Yeah, the thing was there. So what I'm going to do is I'm going to add a little bit of double layer capacitance, and I'll simulate this again. And so this is kind of what I was talking about. This is what, for example, this is like perfect rectangle. It's a bit silly, but if I'm trying to measure this capacitance, this is like, in this case, it's like this double layer capacitance in a non-faradaic region. It's like my starting, again, you said that they don't align, but it's like the start point and the end point. Like the start point is up here, and then I scan negatively, and then it comes down here, and then it comes back. And it's like the start and end point on the x-axis is the voltage, so you just make those the same. And the current should be different. It should be, I said it backwards, so this is the bottom, and then it goes up here. But anyway, the point is that it should be, the current should be positive and negative depending on which way you're scanning, because you're charging up the capacitor, and depending on the direction you're scanning. And then the calculation of that capacitance is basically the I is equal to C times, C is equal to the capacitance is equal to the current times the scan rate, basically. So I unless what you mean by like it's not aligning or something like that is something else, I'm not sure what you mean by the start and end point not aligning, because if it's like the current isn't going to be the same, it's supposed to make like a rectangle or whatever, that's normal. So unless you have a sort of a clarification, I wanted to just show you like that's what that behavior is supposed to look like for like scanning a non-faradaic region to probe at capacitance. So anyway, I hope that answers that to some degree, right? But again, clarify if you're seeing something different and I didn't understand properly.
Yeah.
There's a lot here from Gultikin, which I think we've covered all that. Yeah. So hopefully you'll work on the best method. Okay, perfect. Yeah. Hopefully you get to the bottom of this membrane conductivity test. It looks like Envious Prenit has a question. In the equivalent circuit for EIS with a resistor and a CPE in series. Oh, in parallel, he clarified, or parallel. Okay. A resistor and a CPE. Does the value of the CPE here suggest the extent of the double layer strength, and in turn the amount of charge accumulated on the electrode? Kind of, yeah. I mean, basically that's like if you have a Randles element, so you have a resistor and a CPE in parallel, for instance, the resistor is related to the charge transfer resistance of some process, faradaic process, presumably. And the CPE is the double layer capacitance, which is, double layer strength, or whatever you want to call it. It's the capacitance of the double layer, that is the charge accumulated at the electrode. I mean, the double layer capacitance is the inner Helmholtz plane, basically. Yeah, I guess that's charge accumulated. I guess is that synonymous, basically? Or not exactly.
I've always thought of the double layer as so they want to know extent of double layer strength, and in turn the amount of charge accumulated. So I think you can, like, if you get a capacitance value and you know the voltage with which that capacitance was calculated or taken at, then you can determine the amount of charge at the electrode. So the way I think about it, at least, this is assuming you're in a non-faradaic region. I'll actually just, I mean, this is at least how I think about it.
Yeah, because the
Like if I
like
have
the farads of capacitance you measure times the voltage gives you the charge.
gives you the charge, yeah. So
yeah, in theory that
so
would work.
so any charge, like all this stuff here, these circles I'm drawing, this is double layer. I'm just making it up. There's there's some minus charges, there's solvated, blah, stuff like that. But this is all to say that there is charge balance on one end. All the positive charge on one side has to be balanced by charge on the other side. That's how it works. So if you can get let's see, so what capacitance is charge in Q per volt. So if you know the voltage that if you did EIS are centered around your EIS baseline, you know the voltage, and then you know the capacitance via the CPE, then you can determine the charge of the electrical double layer for that capacitor. I think that's a fair way to determine how much charge is accumulating at your electrode, assuming there's no faradaic reactions occurring, because then your charge is different. Your charge is very different if you have reactions occurring. But and it's just balanced. So it's balanced at the inner Helmholtz plane. It's balanced at the outer Helmholtz plane. That's like over here and all that stuff, and then whatever little diffuse layer stuff that might be happening, it'll be balanced with that charge ideally. So hopefully, I hope that kind of helps. Yeah. The strength, double layer strength, yeah, if you want to quantify double layer strength by its capacitance, then yeah, that's the way to think about the strength of it. So yeah, I would say that. I don't have any other things. I'm looking for other I don't know if we have time for another question or not.
I think there's one last little question about hysteresis.
I don't know the accumulator.
I think they mean battery.
Oh, okay, battery.
I think they mean a battery. So the hysteresis of a battery.
Okay.
Please clarify if that's what you mean. If accumulator, if that, I think I just sort of, ran a quick search in a translation thing, and I think I'm not sure exactly what language. Please clarify if you mean a battery hysteresis, like a charge-discharge hysteresis. I'm looking at one quick thing here.
So he's saying an accumulator is a rechargeable battery.
Yeah.
And
okay, so it's a rechargeable.
Non-rechargeable is battery, I think. I guess.
Battery is non-rechargeable. Accumulator is rechargeable. Oh, okay, interesting.
Yeah.
So battery. Yeah, in English we just tend to say battery for both, and you have to say whether it is rechargeable or not, or we say primary or secondary. Primary, meaning non-rechargeable, and secondary meaning it is rechargeable. Okay. Yeah. So I think that the short answer is it is a diffusional effect. It's a bit of a curious thing. I actually there's papers that talk about this phenomenon like at length. It's I think it's largely I think it's largely related to a diffusion, and it's something that is more exaggerated. Let me pull up. I'll just draw it so I can show you what I mean. I mean, first of all, I'm not 100% sure I know what the exact answer is, but effectively, when you're charging a rechargeable battery, this is voltage, and this is capacity, for example. So milliamp hours or milliamp hours per gram. And so when you're charging a battery up, you might have something like this, and when you're discharging it, you might have something. Which way? I think it might be. You'll have something like this, just for instance, and then they'll coincide at the end again. And so this gap right here, right, that is this gap between charge and discharge is called the hysteresis. I think it has to do with diffusional effects. I'm trying to kind of just see. There's a lot of papers about this kind of thing, but generally, what the other thing I'll say is that if you charge or discharge really fast, the difference will be much higher. So, like if this is like 1C, so if you did like 5C, you'd probably get like, sorry, my finger slipped. That's not supposed to be a spike. You'd probably get like an even bigger hysteresis at a faster scan rate. This might be the other way. The charge might supposed to be on top. I think I drew it backwards. So apologies for the thing here. But in any case, the difference between the charge and the discharge will grow at faster scan rates. And you can think about it as kind of a faster charge rates, excuse me. And you can think about it probably in a similar way that like if you're doing cyclic voltammetry, when you scan faster, the double layer thickness grows. Right? Is that right? Did I say that right?
It does.
Yeah. Thank you. Okay.
I
was making sure
you have a larger capacitance.
Yes, the capacitance so the double layer grows. Yeah. So like diffusional effects are more severe or something like that. You're doing it quicker, and so there's it's also related to IR drop, I think, as well. So like even a battery has some IR drop, and so if the like voltage is V is IR, so if I is bigger, the voltage, for whatever resistance is greater. Like it's like the difference between the open circuit voltage and the measured voltage during an experiment. I know I'm talking through a lot of concepts kind of quickly, but something along those lines is a bit of an explanation as best as I can tell. And so again, to that point is if you do a really fast charge discharge, you have a bigger hysteresis. So if you were to do a really, really slow, like C over 10 or C over 20, like a really, really painfully slow charge discharge cycle, you'd probably have almost no hysteresis in theory, because you'd be relaxing everything so much by very, very slowly charging and discharging. Your hysteresis would shrink to almost nothing in theory. But
hopefully that's helpful.
It is a bit of an odd phenomenon. Like I'm just I feel like I touched on this when I was in graduate school. I'd have to even look through my own, like my old work and stuff. And I'm trying to just, look through some publications to kind of remind myself some of the concepts. My memory of this, to be honest, is that it's something that a lot of people talk about and just sort of like, it's because of this, and they just move on. It's like, it isn't,
it's
maybe
not the point of the paper.
Yeah. And it isn't really always known 100% what it's just, it's some hypothesis kind of a thing. So it's a bit of a strange effect, I will admit.
But you're when you're charging and discharging the battery, you're just setting the current, right? Like a constant current.
Usually you're setting a constant current and you're watching how the voltage changes.
So the hysteresis, so you'll get less hysteresis if you make it a slower rate by setting a lower constant
current.
current. Okay.
Yeah.
Okay.
Yeah, the like the you set a constant current, the voltage is changing because the chemical composition of the anode and cathode is actively changing as you're intercalating or
okay.
deintercalating one. You're
Yeah.
basically sending lithium ions, if it's a lithium battery,
Yeah.
sodium, whatever, from one to the other, right? One of them is oxidizing or losing lithium ions in its chemical structure. The other is gaining, and those voltages are changing between the two.
Yeah.
And so the voltage is changing. But there's also an IR drop associated with
Oh.
the it's got electrolyte, and it's not a very high one. It's pretty low. Generally, batteries have a pretty low IR drop, but there's still some there, and so that that current is associated with a drop in the voltage, and that's what can lead to like when you're charging a battery and its voltage is going somewhere, and then you release the current, the voltage drops a little bit. It'll by some amount.
Interesting.
Because it's just an IR drop thing. So I think the hysteresis has something to do with that. The tricky thing is it's just that it's that phenomenon that as you charge, it hits a plateau, and then it kind of shoots up. And as you discharge, it hits a plateau, and where those plateaus are just different.
Yeah.
Depending on whether you're charging or you're discharging. And so it's either it's again a diffusional thing, or it has to do with like for the cathode, for instance, as you're charging the cathode, lithium is leaving it. And so charging up the cathode, it has a voltage curve itself associated with its lithium content going from, let's just say, 100% to 0%. You're charging up, the lithium is leaving the cathode. So like LiCOO, lithium cobalt oxide or something, right? LiCOO2 goes to just COO2. It's not exactly, but let's just pretend, right? So your lithium is going from like 1 to 0. That fraction of lithium in there, it's losing lithium, and that there's a voltage curve associated with that. Like the potential of LiCOO2 versus whatever is something, and the voltage of Li 0.5 COO2, right? Whatever is a different voltage, and then Li 0.1, as the concentration of lithium in the material goes down, and then similarly in the anode, it's the other way. As you're charging it, lithium is going in, and so you have basically carbon, right? And so you have LiC, it's like C6, but so you go from Li0, like 0 lithium, to like Li 0.2 and Li 0.5. And so there's a voltage associated with that. And the voltage of your battery that you're measuring in your charge-discharge curve is just the difference of those two.
But like in the discharge curve, there's like a plateau, right? Right. But during that charging and that plateau, your lithium content on either side is changing, right? So it's only at these edges that like the voltage is actually changing because the lithium concentration on either side of the anode and cathode is changing.
The voltage is changing for the battery itself because the amount of lithium in both of them is changing.
It's changing.
And so the voltage of the battery is the difference between those two. And so like if the voltage is dropping, it's because either it's the voltage of the battery is like cathode minus anode voltage, whatever. It's the difference between the two, right? And so if the overall voltage is decreasing, it's because the cathode voltage dropped or the anode voltage increased. So the difference goes down by some amount, right? And then over a very wide range, for whatever reason, there isn't much change in voltage as you're that's basically how batteries sorry, it's like a tickle in my throat. It's kind of annoying. Anyway,
we're almost done.
We are, yes. I'm talking through this forever, I know, but the voltage is not changing either because both of them are increasing at the same rate or decreasing at the same rate as the lithium is moving. It's just a consequence of the phenomenon. Yeah, exactly. Anyway, so I hope that's, I don't know, some information for you. Something related to that, I think, is also a possible explanation of the hysteresis, because on either side, you have like 75% lithium and 25% lithium of, anode and cathode. And on the other side of your discharge curve, it's the opposite. And the voltages associated with both anode and cathode on a lot of factors, how much lithium is in each of them, whatever.
Mhm.
And it's just this phenomenon related to that IR drop and the diffusional effects and associated amounts of ion in both sides that they don't line up
Yeah.
properly.
Mhm.
Something like that.
Hmm,
But
okay.
I don't know how much better I can explain it.
Yeah, no, it's it can be complicated, but I think that was good. I think that was good.
And I guess we're gonna call it there. So,
Yeah,
we've gone a little
sorry.
over, but we
We've
do
gone a little
appreciate the
bit over.
questions. So
Yeah.
Yeah.
So next week,
I guess
it'll just be you.
I think I'll if,
maybe,
if I'm able
if
to,
you're
I
able
will.
to.
Yeah, but
I will be at the ECS meeting in San Francisco. So if you are there, please stop by the Pine Research booth. You'll be able to see me. Didn't mention that earlier, but that's okay. And we'll let you know on YouTube. Follow us on YouTube or Twitter to know whether or not there'll be an upcoming episode. Just because our spring summer schedule is quite wild.
it is. It will be a bit off and on over the next couple months or 3 months or
Yeah.
a while.
Yeah.
I suppose we will do our best to show up, at least one of us, when we can.
Yeah.
I don't think Alex and I will be in the same room for the next year.
Few weeks, probably.
But if we are, we'd be
Yeah.
happy to join you.
Yeah.
And we do appreciate everybody's questions and everything.
Mhm.
And
we'll see you. We'll see you later.
We'll see you when we see you, I guess. But take care, everybody.
All right. Bye.
Bye-bye.